The next topic in our math review is going to be the method of Lagrange multipliers. So, to use the method of Lagrange multipliers, let's first consider that we have some generic function where, let's say we have f of x is equal to x squared minus 4x is equal to 0. If we wanted to find the maxima and minima, we would normally take the derivative. So f prime of x would be 2x minus 4. Then we would set that equal to 0. So we would have f prime of x equal to 0, which means that 2x minus 4 is equal to 0. Then we would solve this for x, and so therefore 2x would equal 4, and x would equal 2. However, if we want to find the maxima and minima under an additional constraint, such as x squared minus 2 equals 0, then we're going to need to use another method, and one of those methods is the method of Lagrange multipliers. As an example, let's suppose that we have a function f of xy that we want to maximize given the constraint that g of x and y is equal to a constant. The method of Lagrange multipliers says that our roots must satisfy a lambda function of x, y, and little lambda must be equal to a function, the original function of f of x and y, minus lambda times the constraint function set equal to 0, where we have lambda is equal to the quantity g of x and y minus our constant. Again, I've just taken my constraint and I've set that equal to 0, and I've plugged that in and multiplied it by lambda. Okay? Now, in this case, lambda cannot equal 0 because we want to make sure that our constraint is still applied to our function when we're doing our maxima and minima. Okay, so as an example, let's maximize the function of x and y equals x plus y, with the constraint that x squared plus y squared is equal to 1. Using our method of Lagrange multipliers, we know that big lambda must be equal to our function minus lambda, our little lambda, times our constraint equal to 0. So therefore, lambda must be equal to our original function, which we said was x plus y, minus lambda times our constraint set equal to 0. So that would be x squared plus y squared minus 1. And then all of that must be equal to 0. Next, let's differentiate with respect to each variable and solve for the individual variable. So I'm going to take the partial derivative of my lambda with respect to x. That will give me 1 minus 2x lambda. I'm going to set that equal to 0, and then I'm going to solve for x. So x is equal to 2 lambda. That's going to be my equation 1. Then I'm going to take my partial with respect to y, and so I get 1 minus 2y lambda. I'm going to set that equal to 0. Solve for my variable, which in this case is y. So y is equal to 1 over 2 lambda. That's going to be my equation 2. I'm also going to differentiate with respect to my little lambda. When I do that, I will get negative 1 times the quantity x squared plus y squared minus 1. I'm going to set that equal to 0. And then I'm going to solve. And therefore, I get negative x squared minus y squared plus 1 equals 0. I then multiply by negative 1 to get x squared plus y squared minus 1 is equal to 0. And that is my equation 3. So now I have 3 equations and 3 unknowns. So I'm going to plug in equations 1 and 2 into equation 3. So I'm going to plug in x and y. And therefore, I will get just a function of lambda. So I have 1 over 4 lambda squared plus 1 over 4 lambda squared is equal to 1, which then simplifies to 1 over 2 lambda squared is equal to 1, or 2 lambda squared is equal to 1. Therefore, lambda is equal to plus or minus 1/4. And therefore, x is equal to 1 over plus or minus the square root of 2, or square root of 1/2. And y is also equal to 1 over plus or minus the square root of 1/2. Now, the reason that I want to include my plus and minus is because remember that sometimes the plus and minus will give us different maxima and or minima. So, therefore, by evaluating those positive values of x and y, that will maximize my original function of x squared plus y squared is equal, maximize my original function of f of x and y, where x plus y is equal to my f of x. So the maximum will occur at the positive values of those roots. All right, so that will be our method of Lagrange multipliers, which we will use later when we're discussing our statistical mechanics related to our canonical ensemble.